Xia Gu from BIMSA, and he will speak about the integral representation of irregular conformal blocks. So I think Xia is visiting us still for this week, no? Or
yeah, I'm in Italy till this week, but
okay.
I will leave earlier.
Okay. So please.
Yeah, thank you for the title and for Gabriel for its technical support. And yeah, my talk is about the integral representation of the irregular conformal. So we will start by explaining what is irregular conformal. In a 2D CFT, we have a solo algebra, and it looks like something like this. Like the plus such a term. Yeah, a bit maybe I'm a bit sloppy about the term here, but it's basically like this. And the irregular vectors, like it is an eigenvector of positive mode of this Virasoro mode. And in particular, we are focusing on rank 1 states. So we have so the rank 1 irregular state is the simultaneous eigenvector of L1 and L2. And we have L1 acting on I is 0 for n greater than n greater than 2. Yeah, and there is another parameterization apart from lambda 1 and lambda 2. You can use beta and alpha instead of lambda 1 and lambda 2, and it will give us L1 acts on I is beta q minus alpha, and L2 acting on I is minus beta squared over 4 greater than alpha. And here derivative. And using these three, we can verify that the commutation relation is indeed like the one written here. It's L1 I and L2 L0 is double L2 I here. Delta? Q. Oh yeah, I forgot to mention. And Q is the parameter in the CFT. In Liouville theory, we usually do this thing. Q equals B plus 1 over B, and the central charge is 1 plus 6Q squared. And also delta alpha is alpha Q minus alpha. So in this parameterization, we can compare with the primary field. If beta is 0, this delta alpha is the Euro conformal dimension of the primary field. Yeah. And this is the setup. So we can construct a field IZ such that I0 acts on the vacuum is this irregular vector.
So the beta and alpha are just the different parameterization of lambda 1 and lambda 2. You just
yeah. L0. Yeah, so this section means
yeah, maybe you have a parenthesis. Delta alpha plus beta beta.
Oh yeah.
Yeah. Okay.
Yeah, I can write it in this way. Is this good? So this delta alpha.
is always a function of beta, I guess, not only now.
Yeah. You can just write beta here.
And that's fine. So it's not a big one.
Okay. Yeah, and if we assume there's such a field, I say such that this holds, and in the free theory we can construct such a I as a normal ordered exponential to alpha chi z and times exponential beta partial chi z here. Yeah. So in the free field theory, we use chi. This is the free boson. And again, if beta is equals 0, this is the Euro primary vertex operator. Yeah, and we know the energy momentum tensor in the free field theory to be like this.
So you are giving a free field theory realization of the
Virasoro algebra.
Or what is it?
Or the not the Virasoro algebra, but the state of the field.
No, but what this free boson has to do with this blackboard has to do with the first blackboard.
Yeah, I mean, if I have such a field here,
yeah,
and acting on the free field on the vacuum here, I can get an I which satisfies the upper dimension, upper blackboard. Yeah, and I need to say prove this.
Okay.
Yeah, and TZ looks like this. We can do a OPE.
So T of Z is energy momentum tensor, which corresponds to the original restaurant.
Yes. Okay. Original Virasoro algebra. We have only one Virasoro algebra, so that one. Yeah, that one is not changed, but the field is changed now. So the OPE can be done by the, say, this is the free field, so we can do the weak contraction, and I will write the result here. There is a fourth order pole, and beta q minus alpha. There's a third order pole, and conformal dimension over second order pole, just as in the primary case. And there is a derivative with respect to beta, IW over Z minus W squared plus partial W IW Z minus W here. And basically, we are using the weak contraction, and the conversion we use here is that the 2-point function of free boson is equal to minus 1 over half log Z minus W. This is the conversion. So we can do the weak contraction to compute this. And once we have the TIOPE, yeah, we can do the Euro contour integration to get the we can plug the OPE here and get the action, and it is indeed in the form of the definition there. And L2 I and L0 I similar. So now we can safely say this field here is this field here is the irregular, rank by irregular field. Yeah, and we know in the free field theory, we can directly write the correlation functions, any point functions explicitly. And here we do the similar thing, but we add the irregular field here. And usually the primary field's correlation function is some polynomials about z. But if we add an irregular field here, it will be modified into something like this. Zi minus Zj to the 2 minus alpha. This is the Euro piece, and here is the contribution from the irregular vector, which this is the primary. Yeah, we can write it here. Yes, this is the, well, convention is there is a 2 here. Yeah. And the piece here, the new piece here is the exponential of I beta over Zi minus Z. And this is true if all the momentum adds to Q. And otherwise it is 0. Yeah. Yeah, this is the story in the free field theory. Now we would like to say something on the Liouville theory or more general case. In Liouville theory, we cannot do this, and the correlation function, we don't know what kind of form it looks like. But we have the word identity, so we can know partial information from the word identities of the irregular correlators looks like. And now, for example, in Liouville theory, the simplest correlation functions we would like to study is the 2-point function. A 2-point function, for example, phi z1 and I z2. This is the primary with momentum alpha 1, and maybe I should write I alpha and beta z2. And yeah, we can do the word identity story. Namely, this is L0 and phi z1 alpha beta z2 0. If we act on -1 mode of L1, this will equals to 0, and the left-hand side we can do a commutator, and it is like this: phi plus this one phi. Yeah, and this looks like partial z1. Yeah, let me define this as g z1, z2, and beta. Partial z1 plus partial z2 is g, x on g, and this is 0. So this is the L-1 word identity. And we have 3 word identities in total, because the L-1, L0, and L1 x on 0 equals 0. This is the symmetry, global symmetry of the vacuum. So we can get 3 equations. 3 equations. First is partial z1 plus partial z2. This one is 0. And we have L0, which is z1 partial z1. plus Z2 partial Z2 plus delta 1 plus delta alpha plus beta partial beta. G is 0. And the third one is corresponding to L1 is longer. Z1 plus Z2 plus 2Z2 delta Z1 delta 1 2Z2 delta alpha plus beta Q minus alpha plus Z beta partial beta acting on Z. G is 0. So if we solve this equation, we will finally see this partial differential equation can be solved to this form. Arbitrary function of momentum and momentum alpha 1 alpha times e to the beta z1 minus step 2 times beta delta 1 minus delta alpha times z1 minus z2 to the minus 2 delta 1. Yeah, I believe this is the form. And yeah, unlike the primary case, we can't fix this. Yeah, but if we take the limit of beta equals 0, we can see this reduced to the Euro primary 2-point function. Yeah. Yeah, and we would like to proceed in this way to get a 3-point and a higher point function, but they have more parameters, so we cannot solve the quadratures in this way. And instead, we proceed to consider this primary field alpha to be degenerate. In that case, we can have BPC equation, so we can solve it explicitly. Yeah, and yeah, I should write here. So the degenerate fields means the momentum of alpha is equal to 1 minus r over 2 times b plus 1 minus s times 2b. And r and s is in the is greater than 0, greater or equal than 0. Yes. If we restrict the alpha to this case, we can directly write the conformal blocks of the corresponding correlators using integral form. And this integral form is also known as the Coulomb gas representation. And here I write the generalized version that involves the rank 1 irregular field. And this is equal to of integration on some integral contours, which we will explain later, and times of multiple integration over the screening charges, which we insert here. Alpha R1 S1 Z1 dot to alpha beta Z. But the integration here should the integrand here should be evaluated in the free theory. So the coordinates in the Liouville theory can be written as an integration of that one from the free field theory. And yeah, this looks. I need to.
What are the expectations of things when the dimensions in this calculation? Because if it is just irregular or something from the boson, it will impose some scaling conditions for calculations from this.
You mean the conditions on the momentum?
Yes.
Yes. So the that is the same here. So here we have screen charges, momentum, and the well, I don't know if maybe n times the screen charges plus all the momentum here plus to the irregular alpha here should equal to q otherwise. So we should choose the number of screening charges such that this one holds. Yeah. So this alpha is exactly the same thing in the primary field case.
Structure so broad TWI.
Here there is a I WI. Yeah. Yeah. So we can have multiple screening charges. Yeah. Yes. So to avoid the clutter of notation, below I will talk about the simplest example of this expression. Now we consider the simplest degenerate field, which is alpha to 1, and this is equal to 1 minus 1 over 2b, and 3-point function v1 to z1, v1 to z2, and irregular vector alpha beta z. And this can be, according to this formula, be written as z1 minus z2 to the minus 1 to b squared exponential of z minus z1 beta to b. Yeah, and exponential z minus z2 beta over 2b, and integral of dw w minus z1 over b squared w over b squared, and to the exponential zw. Yes. Yeah, we should check the this neutral charge condition, and here the here we have 2 alpha to 1, and this is 1 minus 1 over b, and the screening charges we only use one screening charges, and the momentum of that screening charge is 1 over b. So here the alpha should be equal to q. yes, then you add them up, you get the condition here. And this is the 3-point function. This 3-point function, yeah. If we send the irregular coordinate z to infinity, we can get something interesting. And by sending the irregular singularity to infinity, we really mean we need to do a computation like this. Yes, now the I be sent to infinity and it becomes a bra here. And these two are still in the finite region and acting on 0. And we define this to be V12, V12, I in the infinity. Yeah, so I claim this to be equal to a z1 minus z2 minus 1 over 2b squared exponential lambda to be z1 plus z2 and the integral over dw w minus z1 1 over b squared and w minus z2 1 over b squared exponential to the minus lambda b over w. I secretly changed the parameter of I of beta to the lambda. Yeah, so now lambda is the beta here, but now it's in the infinity. And yeah, although I write the expression here, I didn't actually prove this is the right expression for this conformal block. And to prove this, again, we need to prove it satisfies some differential equations. And we write the differential equations to be proved here. Yeah. Now I let this to be G. And the first equation is again the translation invariant. And the second one is dilatation invariance. Now the irregular vector is sent to infinity, so somehow the lambda beta partial beta becomes get a minus sign. And 1, 2, 3. The third one is the null state equation. Null state equation, which I get from the degenerate field. Minus this one x on G is 0, right? So now I need to prove this thing satisfies this 3 equation. To do this, we first need to specify the integration contour here. And let me call G f times integration of G over dw. F is the this part, this non-integration part, which depends on 3 parameters, and G is z1, z2, lambda, and w. So we take the integration contour gamma to be symbols. And what is symbols? So now we are doing integration on W plane. This is W plane. And first we find the critical points of G. Critical points of G. This is partial G, partial small w is 0. Critical points I denote it using sigma. And now we have the critical points on the W plane. We should solve steepest descent equation of parameterized flow Wt. So let me consider parameterized flow Wt, and Wt satisfies its complex conjugate is equal to minus partial log G partial T partial W, and also its complex conjugate dW dt is minus partial log G partial W, and T is from minus infinity to plus infinity, and also W minus infinity. The boundary condition is this flow will starting from the critical point. So we don't really need to solve this, but schematically, this Wt will look like a flow generating from the critical point, and it will goes to somewhere in the infinity. And there are two such flow, one in this direction and another in that direction. And the symbols are just the joint of this line. So maybe we can use a yellow line. And this is the symbol. Symbols, we use a J to denote the symbol. So this is merely an addition of this line and this line. And what is special about this symbol? Because this is the steepest descent. Descent flow. In the asymptotic region, W, maybe plus or maybe plus infinity. This will goes to 0. So the integrand here will approach 0 in the two endpoints of the integration contour. And also the integration of this G will concentrate on the critical point, the contribution from a critical point here. So it will look like proportional to the G, Z1, Z2, and W taking the value at the sigma number. Yeah, this is these two property will be important in later. Yes.
So you have in mind like a large B expansion?
Large B expansion.
So these are symptotic modes where B is big.
Here you mean?
Yeah.
Yeah, when B is large, this kind of thing is more clear. Yeah. B is small.
So you have to write the specific regime of V, which is asymptotic force. In saddle point, you should have like some large parameter.
Well, I mean, if this is a exponential, if this is a exponential, that one, the first one will hold, right?
I mean, just the regime of the validity of this asymptotic.
Exponential just goes to zero when we approach zero power class, right? It's only about this, not about the.
Yeah, I don't know about the question, but I think B can be quite general, no? In this case.
So you're doing the saddle point in which parameter? This is the question. If it's not B.
If it's not B.
Where's the saddle point?
Sigma is the saddle point.
This is studied around the trigger points, no?
But it is not just some integration task. It shows some integration control shows in such way.
So he defines the integration contour in terms of this
Critical points.
gradient flow lines, essentially.
Yeah.
Okay.
Yeah. I don't know. Maybe this line is problematic if we take a very large B, say. Yeah, but let me first prove this equation, and it will only use thing here. Yeah, and we will turn to this later. No. Well, this one. In this example, we have 2 critical points. So we can write another one here, C1 and C2, and there is a similar symbol here. And this is G1 and this is G2. So these are 2 conformal blocks. So the space of conformal blocks here is 2-dimensional. Yeah. So either case, it's a solution of this equation. Yes, we need. Yeah.
Do we have some special parameters of height? Because maybe it's in the so for the height parameters this space should be the right?
Sorry, the generic case, you can't even write the integration.
But it should be zero because V12 gives V1 stay and identity.
You mean the?
Could you explain why this two-dimensional? Because if we consider if we take this space of conformal blocks, we first use V12, it seems that we get an identity operator and V1 straight. So what are these two conformal blocks in this space?
You want to draw a diagram like this, maybe, and count the dimension here. I don't know if the states in the infinity is not the irregular state, it's 1/2, and 1/2.
One state is one corresponds to identity operator, another one corresponds to some part of variables. Right?
Yeah, I mean, for the regular case, I think the 3-point function it's just 0. Yeah, but for the now we are considering the irregular conform blocks. So something happens, and I'm not very sure about it. But the solution to this equation is two-dimensional. So I think this is two-dimensional conform block space. Yes, we want to prove this, and yeah, it's straightforward, but a bit laborious. First, we need to do the compute the partial z and this one directly on the g part, and this will give us minus dg plus lambda over b dw. And this is minus lambda over b f. And since g is a multiplication of f and integration over this one, now with sum these two, we'll get this one will equal to some integration over the total derivative of g. But since the total derivative of g, since g goes to 0 in the two endpoints of integration contour, this will be 0. Yeah, and other two equations can be proved similarly. Yes. This one, I omit the intermediate step, but will become also a total integral over wg, and this is 0 because of, again, of the asymptotic property. And the new state equation is of second order, so it's trickier. But we can also do it respectively on f and g, and then combine it to get 0. First, by direct computation, we can see this is 0. And now I will call this one a big D differential operator. Now dg is something of a mixed derivative of f and g. Yeah. So there's a second order derivative on g, and we can use the integration by parts to split it into first order derivatives, which I will do here. this is equal to, and by integration by parts, this is the boundary terms cancels again because of the symbol property, and this thing can be splitted. Yeah, so we split this fractional into the difference of two fractions, and the difference of two fractions is the difference of two partial derivatives. So we reduce the second order derivative to the first order, and it happens that these first order derivatives just cancels this term. So dg is 0 here. Yeah. And we can now safely conclude that this one is really the conformal blocks of two primary fields with an irregular field in the infinity. And now we proceed to compute the monodromy of the conformal blocks. And we know the conformal blocks is a multi-valued function, as you can see from here. And the full correlation functions should be a single valued function. So we need to combine the left and the right moving sectors to get a singular valued function. And for this purpose, we can compute we should compute the monodromy of this conformal blocks. And this is done by deforming the integration contour here. The integral representation is particularly useful to compute the monodromies. And now let's see how to deform the contours now. Yeah, so we will use the example. We will also use this example, which is, I forgot to mention, and this thing can be converted into some modified Bessel function. Let's say this is equal to z or proportional to z over b squared and 2 of k of and k is the modified Bessel function. Maybe you cannot directly see from the integration representation, but somehow we can change the. Yeah, here I have used it. This is z1 minus z2. It's the difference of two insertion. Yeah, we can do some. In principle, we can do some integration variable change to get this result. Yeah, and that's just a comment. now we want to do monodromy, and again we will look into the symbol here. For this function, again in the W plane, the symbols looks like this: 0 to z and z to some infinity point. And this is, I name it J2, and this is J1. We seen that this thing is 0, so we can consider just G as a function of difference of the insertion point. So we will now just set this one as Z, and this is not strictly a straight line, but just schematically a line from 0 to Z and Z to infinity. As I said, symbol is a gradient flow from the critical points, and to see this, you can just maybe solve the gradient flow equation numerically and get the critical points and plug in some special value of Z, and then the flow looks just like this. And we will do monodromy, and monodromy is a continuation around the singular point, and now the singular point is 0 and infinity, and we will do the monodromy around the 0, and now G is F times the integration of G. So the monodromy will act on two parts, on the coefficient part and the integration part. Coefficient part is simpler, just multiply 2 pi I to the coordinate z here, and it will give e to the minus pi I over b squared f. Yeah, I believe this is the case, and this means
there is a part which depends on Z1 plus you see, in the second line.
here?
Yes.
Then
Is that also in G, in capital G?
I mean, so we move the function, we move the z1 to 0. So we set z1 to 0 and z2 to z equals to z minus z1. And in this case, here it just becomes z. Right?
So this is a special case.
Yeah. I mean,
Okay.
yeah, but since it's a translational invariant, we can.
But that factor doesn't prove the translation invariant. So
Yeah, it's strange, but
It should cancel the shift of the exponential and the integral, I think. Because the shift the 1, the 2, the shift W, and then shift of W produces some factor which cancels the division from the function. So essentially, this is the function of
the last term you mean? Yes.
here.
Okay. So
Maybe.
it's the translation, the integration variable. Okay.
Yeah. Yeah, the coefficient get multiplied by some phase. Here we define, for simplicity, we define Q to be e to the minus 2 pi I over b squared. So this is written as q1/2 q to the 1/2 f z. And to do monodromy on the integration part is more complicated. We need to consider the deformation of the contour. Now this point z is going to somewhere at the another multi-valued sheet of the multi-valued function, and this is I will denote it as J2 prime. And if we draw the sheeted here, it's like a spiral around the singular point 0, and the J2 is pointing to the lower part of the sheet, and now tilde J2 is at here. Yes, and considering this, the integrand W b squared is equal to I should write it in this way. This thing on prime J2 is actually e to the 2 pi I W b squared on J2 when doing the integration. Yeah, and also W minus Z J2 square is e to 2 pi I W minus Z b squared on the original path. So what does this mean? This means the monodromy effect on G on the integration part is multiplying another phase. So integration on J2 prime is equal to q to the minus 2 J2 GD dot. And because of the integral contour go right up this given surface. And finally, this means if we define the J2 as f times this one, then J2 e to the 2 pi I z is equal to q to the minus 3 over 2 J2z. This is the monodromy of the this conformal block, and we have a.
Zero is the point where the degenerate are inserted.
Yeah.
Okay.
Zero is infinity is the irregular one. Yeah.
Okay. Sorry, in a few minutes there will be another activity here.
Okay.
So yeah.
Maybe just.
Maybe the monodromy around infinity you studied.
Not really. Yeah. Not in this way. I mean.
I see.
Yeah. I'm considering it since the monodromy shouldn't be multiplied to the identity. Yeah. So the infinity will just as the inverse of the monodromy in the zero, right?
Ah, okay.
Yeah.
Because you have just two points.
Yeah. Yeah. Maybe I will just do the integration contour of this one and then just finish it. And okay. So what is G1? And, G1 is a bit complicated because now the new integration contour is like this. Now Z is on the upper part of the sheet, and it first go down and rotate around zero, and then back to the original point of Z, and then going to the infinity. This is the analytically continued configuration of the integration contour of G1. So you can see, maybe I should draw another this kind of thing. This arrow, and this is e to 2 pi iz, and it will first come down from this hill, and then go to this point of Z, and then go here under this slope to the infinity. So this is actually three pieces. This B1 prime, the new contour is J2 prime there minus J2 because the minus sign because of the direction plus G1. So the integration here and the continuation here should include three pieces, and this would be q to the 1 over 2 minus q to the minus 3 over 2 G2 plus q1 over 2 G1. You can see the monodromy is not diagonal. We can write it as a matrix here. Not prime, but e to 2 pi I is q 1 over 2, q minus 1, 2, q minus 3 over 2, 0, q minus 3 over 2 of J1, J2. And this is the monodromy matrix around 0. Yeah. As a last comment, this thing can be compared to the modified Bessel functions just mentioned, and it is the right monodromy properties. Yes. And yeah, to recap, we derived the integration representation of irregular conformal blocks, and I do the simplistic example here, but the actual degenerate the integral representation for degenerate field can be generalized to 4-point, 5-point, and also alpha, not 2.1, but 3.1, which satisfies the third order equation. And this expression we also derived in another paper. And yeah, and similarly, all the monodromy and the braiding and also the Stokes phenomena can be written down explicitly. Yeah. Okay. Next slide.
Questions, comments?
So, first, are you sure that this matrix is conservative in essence, given the phenomenon that this saddle points exchange when you work on this continuation? Because as far as I know, for the Bessel functions, this monodromy matrix is with corrected rows or columns, so that it's determined as some kind of one and trace equals to that element.
Yeah, I think you are talking about the Stokes phenomena. So
no, it is essentially Stokes phenomenon.
Yeah. I mean, yeah, actually, when doing such a, for this one, it's okay. The J2 remains a symbol all over the W. If we grab that and rotate it here, J2 is the symbol. So its expansion around 0 is well defined. But J1 here, you see the configuration is not so good looking. It's not actually the symbol, or its expansion around 0 is not of a good behavior as J1 there. But it's the analytic continuation. It's the true analytic continuation. So you need to differentiate between the formal monodromy and the actual monodromy. Well, maybe. So on this sheet, there's we can draw some regions. Yeah, maybe I should.
Could you write as projects of this conformal movement as Z1 approaches infinity?
As Z1 approaches infinity.
For example, as Z2 is 0, Z1 approaches infinity, or some other normalization. Like, to understand what is
Yeah, I don't know, but yeah, in the infinity, that's the behavior is worse than around 0, and it will surely have the Stokes phenomenon. Yeah, but I don't know if I can write the expansion from the integral representation here.
But is it e to the lambda or e to the square root of lambda? Or e to for which you are studying.
Square root of lambda.
Okay. Then if it is square root, how do you get this matrix without permutation? Because when you perform this monadic inclination, you should somehow switch the two branches of the square root.
Well.
I would write not so on the left because you want to do it. So on the right I would like to write G2 or something of this kind.
I believe you are talking about some Stokes matrices looking like this. I don't know. Maybe acting on the one symbol and like this. Yeah, and you can actually derive the monodromy from multiplying the Stokes matrices and the formal monodromy.
The point is that there are not only Stokes matrices, but also this permutation matrix, which comes from the permutation of the square root.
Well,
and then let's say
yeah, that part I don't know. Yeah. So what kind of branch? So what kind of how to understand such an exchange of the symbol if it is not a Stokes phenomenon?
Maybe it's a simpler way to understand that something should be program along the such matrix is to switch to different values conformal blocks, which is most suitable when Z1 goes to Z2. In this case, this conformal blocks, I think, will have some power levels. And trace of another will put some sign, something like this, or sign of pi over b squared. And this matrix trace equals to maybe.
Yeah, maybe we can talk this later. Yeah. Sure.
Are there other questions, comments? Okay, if not, we thank again.
Yeah, thank you.
Yeah. And it's,
yeah, great pleasure.
I think we should keep them with
It's a cutoff here. Yeah.